I hope. All right. I don't know of many announcements. If any of you are interested in the NASA Community College Aerospace Scholars Program, the deadline for that is the 16th of this month. Okay, we're now into October. So please, it's a great program. We've had several people from Austin participate over the years, and they've all spoken incredibly highly of it. So if you're at all interested, give it a shot. The Scholar Bowl is still receiving or searching for new participants, team members. So if you're at all interested, I don't know if you know where Mr. West's office is. It's down in between room 259 and 261. Mr. Matthew West is the coach of that team, and he'll be glad to meet with you. They meet about once a week to practice, so, and it's always a good time. They have fun, they eat pizza or whatever, and they have a great time practicing and preparing for the Scholar Bowl. There are probably others. I can't think of them now. I'll leave the announcements in the other room and forget to pick them up. So, any questions on anything we've covered so far? All right. We're in Chapter 1, Functions in the Graph, 1.9, Inverse Functions, the last section we're going to do in the chapter. So after we finish this, will be the test. Now, we're off to a late start today. We'll see if we can finish this today. If not, the test will be next Tuesday. Okay? So here's the definition. First, any questions? All right. Yes? Okay. I think it's a great idea to do, so why don't you do your own? Okay? Because, and I think I said this last time, but you may have gone by then, so I'm glad you brought it up. You can bring with you to every test in this course, including the final exam, a formula and equation sheet. Whatever you want to write down on a piece of paper, you can write it down on that piece of paper and have it with you. See, my development for you, you look at it and it's very passive. You develop the study guide for yourself, that's very active. That gets you involved with it more. So yes, you can prepare your study guide. Yes. Yes. Okay. You know the quiz. Okay. The first page is going to be a lot like that. Not the same questions, of course, but similar type questions, same type material. And then the last three sections we've done, 7, 8, and 9, it'll be questions similar to that. Stuff like what your homework exercises were. You know, there'll be about 10 more questions, approximately, maybe a few more. Total of around 20 or 21 questions, doing the things we've done in class and on the homeworks. That's going to be the best thing to do. I'll also point out when we get there, at the end of the chapter, there is a chapter summary on page 104 and 105. Now, we did beginning with section 1.4, going through 1.9. Those list the explanations, examples, review exercises, those kinds of things. Those will be the major things that will be covered on the test. Okay. All right. Now, any other questions? Good questions. We were talking about before what inverse functions were and how you check to see if you have an inverse function. How do you check to see if you have an inverse function or not? Do what? Say again. Okay. You take the composite of the function with its inverse, and what should you get? X. Okay. That's it. Now, here's the definition of an inverse function. We've already been talking about it. Here's a sort of a formal definition. Let f and g be two functions such that f of g of x, that's the composite of f with g of x, is x for every x in the domain. Good. Come on? Yeah. Okay. All right. I've just got to find you then. I know you're in here somewhere. There you are. All right. Any other comments since I called roll? You didn't see me mark your name. Okay. The f of g of x is equal to x for every x in the domain of g. Okay? Here's a little bit of a difference here. And it has to also be true that g of f of x, that the composite of g with f is also x. But that's not quite the same x. This x up here is the x's in the domain of g. The x here is all the x's in the domain of f. Okay? Not in the domain of g. Okay? Under those conditions, if both of those are met, the function g is the inverse function of f. Okay? And the function g is denoted by f inverse, red, f inverse. So the f of f inverse, that's exactly what we have here, is equal to f, and f inverse of f, because f inverse of g, is also x. Okay, the domain of f, this f, that one, must be equal to the range of f inverse. Okay, and the range of f inverse must be equal to the domain of, the range of f, range of f must be equal to the domain of f inverse. All right. Now, that's a definition. However, it doesn't tell you how to get it. Okay? Up till now, we've been guessing. Guessing won't work. With very complicated functions, you'll spend all day guessing and still may not come up with the right answer. But this is how you check it. This is your check to make sure you have inverse functions. Okay, once you have found them. But, okay, here, I've already said this, but I'm going to say it again because we put it on the slide. Do not be confused by the use of a -1 as a superscript to denote the inverse of function, f inverse. Okay? Already got you. Okay. In this text, whenever f inverse is written, and let me just it's not just f inverse. It's any function -1, superscript -1. Any variable, any number, superscript -1 means reciprocal, 1 over that. Not for functions. If f is a function, which it is, f to the -1 is not an inverse, is not a reciprocal function, it always refers to the inverse function of f, not to the reciprocal of f. So don't get that confused. If the function g is the inverse function of function f, then it must also be true that f is the inverse function of g. If you find the inverse one, because they have to go both ways, they're inverses of each other. For that reason, you can say that functions f and g are inverse functions of each other. So f is g inverse, g is f inverse. All right. I believe they're skipping example 2 completely, okay? So let's go back and find some white space. Okay, that looks like some white space. Actually, that looks like a little more white space. So let's do example 2. Which of the functions, let me get my pen set up. Okay. Which of the following two functions is the inverse of f? Here's your f of x. 5 over x minus 2. Okay? Here is g of x. X minus 2 over 5. Here is h of x. 5 over x plus 2. Okay? I don't know what that line is, but it shouldn't be there. Of course, if I erase it, the whole thing's going to go away. Okay. Okay. Now, you might hazard a guess. You have a 50-50 chance of getting it right, unless you're very intuitive. You may have a better chance, but how do you know for sure? Which of these is the inverse of f? Plug them in, plug them in. What do you plug them into? Second? Okay? Well, you plug them into, here's what you're investigating. You're investigating to see what f of what? G of x is. So that's what you plug in. So this will be f of, and what's your g of x? X minus 2 over 5. Okay? And f operating on that, f says start with the number 5. Okay, we'll start with 5. Then draw a dividing line divided by whatever is in the parentheses there. It wasn't x before. Now it's a x minus 2 over 5. X minus 2 over 5. And then subtract 2 from that. Okay? Running out of room, so it's a little crowded down here. G of x is x minus 2 over 5. And f says take the number 5, divide it by whatever's in here. And what's in here is x minus 2 over 5 minus 2. Okay? So we got a little bit of work to do here. Yay! All right. Now, some texts call this a complex fraction. Really don't like that name because usually complex means imaginary numbers. That's not what we're talking about here. I call it a complicated fraction, but then some of you will say, well, all fractions are complicated. Well, no, they're not. These are more complicated than others. So if you have fractions within fractions, find the least common denominator of any of the inner fractions. You only have one, 5. And what you do with that is multiply 5 by your denominator and multiply 5 by the numerator. Well, 5 times 5 is 25. And when you multiply 5 times this, the 5's go out and you have x minus 2. Multiply 5 by minus 2 and you get minus 10. Okay? So that gives us 25 over x minus 12. Is there any way in the world you can wangle an x out of that? No. So g is not an inverse function of f. Okay? Looks like we better hope the h is. Okay? So can I go on and erase g so I have more room to work? Oh, y'all still writing? Okay. I'm sorry, it's messy and confusing. Let me see if I can scoot this way. Does that help at all? Okay. I can pin myself to the wall here. Okay. Is that better? Okay. All right. So G is not an inverse of F. All right, to erase or not? Yay or nay? Yay? Yay! All right. Let's erase the G work. Okay. G is all gone. Okay. Now let's do the same for H. In fact, I think what I want to do is move H if I can. H of x is equal to 5 over x plus 2. Okay, so let me get rid of this down here so we have more room to work, because we like to work. Okay. So what do we do here to check to see if h might be the inverse function? Do f of h of x. And what would that be? F of 5 over x plus 2. And what f says to do is to take that, start with the number 5, divide it by what is in the parentheses. And that is 5 over x plus 2 minus 2. Hey, something that looks pretty easy right off the top. Minus 2 plus 2 adds to 0. And then 5 divided by 5 over x, that's the same as 5 times x over 5. And what's that? X. Ding, ding. It looks like we have an inverse. It looks like we have an inverse. What's the safe thing to do? check it and see if it goes the other way. So what's the other way? We check to see what? We did f of h of x, h of f of x. And what would that be? H of, you tell me, 5 over x what? Minus 2. And then h says to do what? H function. Start with the number 5, we will, and divide that by whatever is in the parentheses. Well, here what's in the parentheses is 5 over x minus 2. And then add 2 to that. Be sure you get your pluses and your lines and everything lined up properly. Okay. First operation here says to divide 5 by 5 over x minus 2. Let's do that off to the side here. Get that out of the way. And that would be the same as 5 times x minus 2 over 5, right? When you divide fractions, you multiply by a reciprocal. Oh, that's a long time ago, wasn't it? Still works, okay? And then we add 2 to that. Well, here, the 5's cancel out, divide out, and become 1. And then you have x minus 2 plus 2. Guess what those do? Minus 2 plus 2 goes to 0. And again, ding, 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 we have an x. So sure enough, these are reciprocal functions of each other. This is f inverse. And this also happens to be h inverse. Okay? So they are reciprocals of each other. There was example 2. And as most of the examples, I think just about every example, there is a checkpoint. Good thing to do the checkpoints as soon as you can after class so you can verify or reinforce what we've learned here and make it yours. Right now you're listening to me talk and you're doing some participating, but when you do it on your own, that's when it becomes yours. Okay. Any questions? Anyone need it a little bit longer? Okay. If not, let me proceed to find graph of a function. All right, graph of the inverse function. Okay? The graphs of a function f and its inverse, f inverse, are related to each other in the following way. Remember when we first started, we said if you take the ordered pairs and reverse the domain and range, you have the inverse function, right? Well, same thing with the graph. If a point AB is on the graph of f, guess what point is on the graph of f inverse? BA, you got it. Then the point BA must lie on the graph of f inverse, and vice versa, okay? Inversa. Okay, never mind. This means that the graph of f inverse is a reflection of the graph of f across the line y is equal to x. That good old identity function. Okay.
Raquel.
Huh? Raquel, got it. Okay. Well, I can't write with that pen, can I? Good deal. Anyone else come in since I called roll? I missed seeing you come in. Okay. All right. Across the reflection across y equals x, the identity function, is shown here. Now, we don't know what the function is. We just know your original function, y is equal to f of x, is this function that starts here, goes up here, and goes here. Well, what you can do is draw the identity function here, y is equal to x. They use a dotted red line, that's okay. Anywhere where one function crosses, the other must cross, because that's a point AB, and BA is, well, this is AA, and this is AA, okay, it's the same point. So they have to cross there. Where this one goes below, this one is above. Here's something to note, though. This function is an increasing function. The inverse is also an increasing function. Maybe increasing at a different rate, but it is an increasing function. And then for every point A, B here, so this is A units here, B units up, go over B units over, and A units up, and you've got the point on the inverse function. For every point there. So they reflect across the identity function y is equal to x. Okay. Now, I think that leads us to example 3. Sketch the graphs of the inverse function, f of x equal 2x minus 3, and the inverse function. Now, we're going to have to take their word for it that it is an inverse function. I think when we sketch it, we'll see it is. On the same rectangular coordinate system, show that the graphs are reflections of each other across the line y is equal to x. So let's do our graph here. Okay? All right. Let me tick off a few points here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Okay. Let's start with f. Let's do this in our black. How do I sketch the graph of that function? What kind of function is this? Linear function. Okay, can you tell me any characteristics of that linear function? Is what? Yeah, the y-intercept is -3. There it is, right there. And what else? Slope is 2. That means you go up 2 for every one you go to the right. Up 2 for every one you go to the right. Up 2 for every one you go to the right. Mine doesn't look very straight, does it? Up 2 for, don't make fun of my drawing. Okay. Up 2 for every one to the right. Up 2 for every one to the right. Oops, that's not far enough. And so on. Anyway, and down 2 for every one to the left. Okay. Let's just say it's a line like that. Okay. Not very pretty. Okay. Now, perhaps before we do any more, let's go on and sketch our identity function. I think I've done a pretty poor job of doing this. Let me do a little bit better. Okay. All right. We have that point, this point, this point. Goodness gracious, it's so hard to see with all this mess on the page. That point, and maybe that point. Okay. Okay, let me get rid of that first line. That wasn't very pretty line at all. Okay. That one's still not very pretty. But anyway, here is the identity function. If I'm not mistaken, it's something like that. Now, I might be cheating a little because I think that point's supposed to be on it. And it continues going down here too. Okay. Y is equal to x. Should be going up through that point there. So let me... Okay. Not a good job of drawing. If you have graph paper, you can make it look a lot better than this. Okay? And let me also get this line so it goes through that point. Okay. Okay. I think I've got it. All right. Now, how about this one? F inverse. What color you want F inverse to be? Pick me a color. Any color. Not red, not black. Green. Say again, green? All right, let's do green. Continue this one down here. Whoa. Green. Dark green? Okay. I want to do that one. Now, that's a little messier to do, mostly because of that fraction, isn't it? Let me write it just slightly differently. F inverse of x is equal to 1/2 x plus 3/2. Still a little messy, but let's do it. Okay? Now, what can you tell me about that function? What kind of function is it? Linear. What characteristics of it? Slope and y-intercept. What's the y-intercept? 3/2. That's 1.5 right there. And the slope is 1/2. So you go up 1/2 for every one you go across. Up 1/2 for every one you go across. Up 1/2 for every one you go across. And looky there, I think we have an intersect. Up 1/2 for every one you go across, and it continues like this. So it does like, ooh, just hit my hand on that. And down 1/2 for every one it goes down. Okay, you got it continuing this way. Whoops, here. So anyway, whoa, that's terrible. Something like that. Ew, that's awful. Okay. The point being that they cross where they both intersect there on the identity function graph. That has to be some point where x is equal to y. Here we had a 2, 1, and the next one would have been a 3, 4, and the next one would have been a, oh goodness, I'm there, am I not? Okay, let's see. Here we're at 0, 3, 0, -3, then we're at 1, -1, 2 plus 1, and then 3, 3. That's where we are, 3, 3, yeah. And sure enough, we are. And on this one, when you multiply both sides by 2, you get x plus 3. No, you won't want to do that. That would give you 3 times 3. But anyway, when you plug in a 3 here for x, 3/2 plus 3/2 is 3. So sure enough, that gives you 3, 3 also. So they do cross, and when one goes, notice they're both increasing functions. Both of them increasing functions. This one's not increasing as fast as that one, but it's still an increasing function. And they cross where they have that common point. And that's on the identity function. 3, 3. All right. Now their drawing won't be quite as pretty as mine, but I think you can live with it. Here it is, f and f inverse. Here's your f function in the gray line here. Started at -0, -3, 1, -1, 2, 1, and 3, 3. And it keeps on trucking. Going up 2 for every one it goes to the right. Or down 2 for every one it goes to the left. And here that is. Okay.
Yoshi.
Huh?
Yoshi.
Wilson?
Yoshi.
Huh?
Yoshi.
Yoshi, got it. I'm sorry, I can't hear worth it. 2. Okay, Yoshi. There you are. All right, good deal. Anyone else come in since I called roll? I missed you. Okay, we're doing inverse functions. This is example 3 in section 1.9, somewhere there about page 86. Okay. And this other one, 1/2 of x plus 3, its y-intercept, and you can't see it well at all here the way they've done it. They put every 2 as a tick mark. See, it's not nearly as pretty as mine. Okay, and that would be 1, so this would be 1.5 right there. So it's starting in the right place. But they picked other points. For instance, if you pick 1 here, 1 plus 3 is 4, half of 4 is 2. So 1, 2, there it would be. And then you go up 1 for every 2 you go, for every 2 you go over, and that would give you 3, 3. And down this way too. So sure enough, they do cross there. They reflect across the identity function. This one goes this way, that one that way. One's above the line, and where they cross, then that one's below, the other one's above. It appears that the graphs are reflections of each other across the line y is equal to 0, the identity function. You can further verify this reflective property by testing a few points on each graph. And just look at them. -1, -5. Here's -5, -1. 0, 3, 0, -3, -3, 0. -1, 1, 1, -1. 2, 1, 1, 2. 3, 3, 3, 3. Yeah, that one's right. So yeah, every one of them flip the x and y coordinates. That was example 3. That's also followed by a checkpoint. Okay, and here's what we were just saying. I didn't know they were going to say it again. Note that the following list is the point AB on the graph of F, and the point BA is on the graph of F inverse. Just like we said, these flip, those flip, those flip, these flip, and those flip, and be the same thing. Okay, because of 3, 3. And you can continue on in both directions, and you still have everything being exactly reflexive, exactly the opposite of the other. That was example 3. They're skipping example 4. So I think we're going to have to go back here and do example 4. Okay? Verify graphically, not the best way to verify graphically that the functions, let me get my, whoa, I'm still in green, am I not? Okay, let's go back to black. Okay? F of x equal x squared. Now this has a limit on the domain. X greater than or equal to 0. Okay? And g of x, which is the square root of x. Verify that graphically that they're inverse functions of each other. Okay, and since x has to be greater than or equal to 0, in fact, I can even bring my vertical line further over, like here, and we'll only deal with the positive values here. Let's tick off a few points. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13. 1, 2, 3, 6, 7, 8, 9, 10, 12, 13. Okay. Not exactly evenly spaced, but we'll live with it. Okay? We're only dealing with x's not negative. So when x equals 0, what is f of x? Help me. X equals 0, what's f of x? 0. When x equals 1, what's f of x? 1. When f of x is equal to, when x is equal to 2, what's f of x? 4. Okay? X equals 3, what's f of x? 9. Okay? When x equals 4, 16, that's off scale. So this is our good old parabola going up something like that. All right, g of x. What color should I do g of x? Not red. Not black. Huh? Blue. Light or dark? Light blue. Carolina blue. All right. When x is 0, 0. When x is 1, 1. Now guess what x I want to do next? 4. Why? Because I can't take the square root of 2, 3. I can take the square root of 4, and what would that be? 2. Well, I want to know what I want to do next. 9. 5, 6, 7, 8, 9. I feel like, okay. Somewhere here, that would be 3. And 16's off scale, so we'll do it. So this goes like this. Now, what line could we draw in here? Ooh, that's not what I wanted. Okay. Also need to put another line in here. What line's that? the y is equal to x, the identity function. Go right like that. Okay? What you reckon? It says, verify that they're inverse functions of each other within this domain. Okay? And sure enough, this one's below the identity function here, but they join at 0, 0, and 1, 1. This one's below here and curves up. This one is above and curves down. And then that continues this way, that way. Sure enough, they do look like they reflect across the identity function. Now, my drawing isn't very great, but it gives you the general idea. Okay. Now, do you see why x here has to be greater than or equal to 0? Because the input here is the output there. And when you see square root of x means principal square root, only positive outputs. So if this can only have positive outputs, this can only have positive inputs. Now that's one reason. There's a more important reason coming up, and we'll get to that later. But secondly, how about the input for this one? Say again? Inputs for this. Yes, they cannot be negative either. So therefore, the output for this can't be negative. Well, of course it wouldn't be, because anytime you square a number, it's going to be positive. So that fits all right too. Okay? Now, any questions on example 4? And by the way, there is a checkpoint. All right. Now we're going to get, yes? Well, what? No, you have to pick those. Yeah. Well, you pick the x and figure out what the y is.
Okay. So
yeah.
You go back and look at your parent function.
Yeah, the original function. Yeah, the f function, right. Yeah, when you have to graph, you have to pick your points and go with that, just like we've done here. Good question. Any others? All right. One-to-one functions. What in the world could we be talking about here? By the way, the hint from now on for this answer will be, okay, got it? All right. You'll need it. Maybe. Most other classes have. Now, the reflective property of the graphs of the inverse function gives you a geometric test for determining whether a function has an inverse function. Now, we already have a geometric test to see whether a function is a function or not. What is that? Vertical line test, okay? But now we're going to do one to see if it has an inverse function. If it's a function, it's still got to have pass the vertical line test. But now we're going to introduce a new one, and guess what? That's going to be the horizontal line test for inverse functions. So here's the deal. Remember I said, notice this one's always increasing. That one's always increasing. You could have them always decreasing, and then the next one would be always decreasing as well. But the test is the horizontal line test for inverse functions. And here's what it is. A function f has an inverse function if and only if, there's no way around it, no horizontal line intersects the graph more than one point. Okay? Now, let's see if it's still up here. Aha, there it is. If we had gotten my pen back, continued this function here and gone up the other side, would that be a one-to-one function? Horizontal line test fails on the original graph there, because the parabola does not pass the horizontal line test. It only does if you only consider positive or negative values of it. Okay? It can't if you include both positive and negative, because then it fails the horizontal line test. So only the positive side. That's why the other reason they chose x greater than or equal 1 to make sure it was 1-to-1. But of course we hadn't gotten there yet, so that couldn't have been your answer unless you knew it already. Is the square root function a 1-to-1 function? Yes, because there any horizontal line it's sort of horizontal line will only cross it once. But a parabola, no. Not unless you restrict the domain. So, That's what we're getting at here. If and only if no horizontal line intersects the graph at more than one point. If no horizontal line intersects the graph of alpha at more than one point, then no y value is matched with more than one x value. That's exactly the inverse, you might say, of what we had for a function. You know to be a function, no x value can have more than one y. More than one y value. Now no y value can have more than one x value. That's what we mean one-to-one. Okay? That's an essential characteristic of what we call one-to-one functions. There's one and only one x for every y and only one y for every x. So one-to-one functions. A function f is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. Exactly the reverse of what the vertical line test tells you about being a function. A function f has an inverse if and only if it is one-to-one. So every one-to-one function has an inverse, and it can have an inverse only if it's one-to-one. That's what if and only if means. Okay. So let's consider the function given by f of x is equal to x squared. Table on the left is a table of the values f of x equal to x squared. Table on the right is the same table on the left, but with the values interchanged, as if they were inverses. Okay? Now, x equal -2, y is equal to 4, right? X equal -1, y is equal to 1. 0, 0, 1, 1, 2, 4, 3, 9. Okay? That is a function, right? No x shows up. You can't have two x's. For any x, you only have one y. Okay? For any x, it's only one y. Okay, now if you reverse them, flip your x's and the y's, 4, -2, 1, -1, 0, 0, 1, 1, 4, 2, 9, 3. Guess what? Yes. Here you have two 4's here with different y's. Two 1's here with different y's. Can't happen. This is not a one-to-one function. Like I said before, a parabola fails the horizontal line test. So that's what this is showing. Seems like to me that would have been easier to show with the horizontal line test than with the table, but the table works too. Okay? In other words, to be one-to-one, you don't need this table. You look here and see if any of these are repeated. They are for different values here, not one-to-one. You don't even need the second table. Okay? But they put it, and it's okay. Table on the right does not represent a function because input x equal 4, matched for two different outputs, -2 and +2. Same thing for 1, it was matched by +1 and -1. So f of x is equal to x squared is not one-to-one, does not have an inverse function, unless you restrict the domain. Restrict the domain to only positive values? Yes, that works. Or only non-positive values. That works, okay? But it cannot work for all values of x. Not one-to-one on the real number system. So here's example 5. And by the way, this one you can go to larsonprecalculus.com for an interactive version of this type of an example. You don't need a code. You don't need anything. Just go there. Okay? The graph of f of x is equal to x cubed minus 1 is shown on this figure. Now this is a pretty easy one to graph. You can either plug in numbers and work, or you could think of your parent function, f of x equal x cubed, which would go like this, and then drop it by 1, because that is a vertical shift downward. Okay? Now, you think that's one-to-one? Sure. It's a function because it passes the vertical line test. It's one-to-one because it passes the horizontal line test. Okay? So that tells you two things about it. It passes the horizontal line test, and what does that imply? passes the horizontal line test,
It's a one-on-one.
it's a one-to-one function. What does a one-to-one function imply?
That's it.
It has to have an inverse. You're absolutely right. Now, we haven't figured out what that inverse is, but we know it's got an inverse because no horizontal line intersects the graph at more than one point. F is a one-to-one function and does have an inverse. Two things you know if it passes the horizontal line test. It is one-to-one. It does have an inverse. Okay. Now, the B part says, how about this one? Alpha of x is equal to x squared minus 1. That looks a lot like, nope, why not?
Because it fails the horizontal.
Fails the horizontal line test the way it's written. If you restricted the domain to be only non-negatives, that would work. Or only non-positives, that would work. But it does not work for all real numbers, okay? Because it's possible to find a horizontal line that does intersect more than one point if it's not one-to-one and cannot have an inverse on that domain. Okay? Make sense? That's what if and only if. It can't if it doesn't. Okay? It will if it does. Guaranteed. All right, that was example 5, A and B. And guess what? There is a checkpoint. All right, so for very simple functions, we've guessed what the inverses are. For graphs of them, we can kind of guess what the inverses are there too. We can also tell whether or not they have inverses. But if we verified it has an inverse, how do we find these inverses if it's not something really simple? That's what we're going to be talking about now. Finding the inverse functions algebraically. For relatively simple functions, example 1, you can find the inverse function just by inspection. Okay? For more complicated functions, however, it's best to use the following guidelines. Now, they say the key step to these guidelines is step 3. I don't like the way they number them, and I'll give you slightly different ways of numbering and stepping them. Okay? Interchanging the roles of x and y. Because that's what we do with inverse functions, isn't it? We interchange x and y. So that's why they say, whatever step you number it, that's going to be key. That step corresponds to the fact that inverse functions have ordered pairs with coordinates reversed. X's and y's exchange. I wonder if I can see it. It's upside down. Okay. All right. So here are the steps. I don't care for necessarily the way they've broken them up, but here's what it is. Step number 1, use the horizontal line test to determine whether it has an inverse function. Guess what? Before you can use a horizontal line test, you've got to graph the function. So to me, number 1 would be draw a graph, or at least think through it, and make sure that it does have an inverse. And that would be either on the graph, doing the horizontal line test, or when you're thinking through it, mentally doing the horizontal line test. So to me, step 1 should be draw the graph, okay? Then, number 2, use the horizontal line test to see whether it has an inverse function. If it does have an inverse function, hang it up. You can't find one, okay? If it doesn't pass the horizontal line test, if it's not one-to-one. Okay, the next one, whatever number you give it. In the equation for f of x, replace the f of x with y. That's been our favorite thing to do all term, right? What is f of x?
Y.
And what is y?
That's
F of x, okay? So you just replace the f of x with y. Pretty simple step, okay? Then the next one. Now exchange the x's and the y's. Okay, that to me should be its own step. Next step, solve for y. Why put this in with that one? Solve for y. See, I would split these up and make them a little simpler steps. Okay? Once you solve for y, replace the y with f inverse. Just like you replace this y with, or this f of x with y, replace this y with f inverse. Because you just swapped. Okay? Then, verify by, this is the fun part, that f of alpha inverse are inverse functions of each other by showing that, number one, the domain of f is equal to the range of alpha inverse, okay? The range of f is the domain of alpha inverse, yes, and the f of alpha inverse is x, and the f inverse of x is x, of alpha is x. A lot to do on that last step, okay? And actually that takes more time than the rest of it, okay? But it's doable. All right, so let's find the inverse function of f of x is equal to 5 minus 3x over 2. Now, frankly, I don't like the way they've written that function. Let's keep the meaning, but rewrite it slightly. How could you rewrite that? Five over 2 minus 3 over 2 times x. How about that? Everybody agree that's the same? Okay, what if we reverse those and say minus 3 over 2x plus 5 halves? How about that? Is that okay? Legal in most states, right? Now, what do you notice about that function? It's a linear function with what? A slope of negative 3 halves. Okay. Now, if this is a linear function with a slope of minus 3 halves, it's going to look something like that, right? You think that's going to be 1-to-1? Yeah. Horizontal line test is only going to cross that once. Okay. Now, if that was this, nah, not. Okay. But any other slope other than 0, a linear function is always going to be 1-to-1, as long as the slope is not 0. How about if it had a vertical slope?
No.
It's not a function, is it?
It's not
Okay, because it fails the vertical line test. The horizontal function fails the horizontal line test, vertical function. But any other linear function, the slope is not 0, then you're going to pass to the horizontal line test without having to graph the function, right? If it's a linear function with a non-zero slope, it's got to be 1-to-1, okay? Because it's going to be either strictly increasing or strictly decreasing. Okay, so we've taken care of the first step or two. All right. Now, we can go back to the original representation of it if you want, or we can stay with that one. But I went to that representation so you could see for certain that is a straight line, a linear function. Let's go back to this one. What's your next step? When we said at the very beginning, what is f of x? Y. So you write that. Y is equal to 5 minus 3x over 2. Now, what's the key step then? Swap them. Okay, so what would that become? X is equal to 5 minus 3y over 2. Now, what's the next step? They solve for y. Excellent. So what is your first step to solve for y? Multiply both sides of the equation by 2. Wipes out that denominator. We don't like our denominator, do we? Okay, so let's write what we've got. We've got 5 minus 3y is equal to 2x. I swap sides too. Okay, now what? Subtract 5 from both sides. I like it because we're trying to solve for y. So these go away, and now we have negative 3y is equal to 2x minus 5. And now what? Divide everything by negative 3. And what you have then is y is equal to, now I'm going to switch sides, not sides, but terms again. 5/3, because negative 5 over negative 3 is positive 5/3, minus 2/3 x. Okay, now I wrote it that way for a reason. The book will write it like this: 5 minus 2x over 3. Either one of those is fine. They're perfectly correct answers. The reason I wrote it this way is to point out to you that the slopes, this one's the negative slope like this one's the negative slope like that, okay? They both have negative slopes, but this one's a steep slope, that one's a shallow slope. Your y-intercepts, yeah, they're different too, but that doesn't really matter that much, okay? But this way and that, yeah. Those are your two. Now, next to the last step would be to change that y to F inverse. 5 minus 2x over 3. Okay. Now, the last major step here is to verify their inverse functions of each other. And that does take a little bit. So what I'm going to do is erase everything else so we'll have room to write. Has everyone got what you need to here? Did I move this more into your way? Lesson? Okay, okay. I don't know if that helps any or not. Everybody through writing? Okay. So let me erase everything I can get away with. I hope I don't erase too much. I want to leave the F inverse and the F. And that's about it. And what's your first test? Second? I can't hear. Can't hear. I can't hear. A little louder. You're talking too softly. I can't hear. The what test? A horizontal line test? Is that what you say? We've already done that. Okay. What do we do to verify these are inverses of each other? Second, plug it into what? We look at F of F inverse of X. That's probably what you meant by plugging in, but I didn't know. So what do we do here? F, we'll deal with that in a minute. What is F inverse? 5 minus 2x over 5. Okay, and the F function says to start with, second, it's over 3. I can't read my writing, okay? I can't hear and I can't read, okay? It's the sad, sad state of affairs, okay? Over 3. All right. So your F function says start with the number 5. So that's going to start with the number 5 and subtract from that 3 times whatever is in the parentheses, which is 5 minus 2x over 3. And then divide all that stuff by 2. Okay? Now, what's the first thing you note you can do? The 3's divide away to 1. Okay? So wipe those out. So let's see what we've got then. 5 minus 2x divided by 2. So what's the next thing you can do? Second? Not FOIL, but distribute the minus sign across the parentheses. So that'll be a 5. What next? What's minus 5 plus 2x over 2. And 5 minus 5 adds to 0. Nice. And then 2 over 2 is 1. And you have x. Ding, ding. We verified at least one way that F and F inverse work going one way. What's this next test? Almost the same thing, but not quite. Yeah, we do F inverse of F. And since I don't have enough room, did I erase too soon? Sorry. We're running out of time, is why I'm kind of in a hurry. f of f inverse, and that's what f inverse of f is what we do next. Sorry if I erased too soon. Okay, f inverse of f of x. So what do we do first? What is your f? 5 minus 3x over 2. And f inverse says start with the number, you tell me, 5, and subtract from that 2 times what? What's in the parentheses? 5 minus 3x over 2, and divide everything by 3. What's the first thing you can do? The 2's divide away to be a 1, and that gives you a 5 minus 3x divided by 3. And now what? Distribute the minus sign across, and what do you get? 5 minus 5 plus 3x over 3. 5 minus 5 is 0. Those disappear. 3 will go in the 3 once, and you're left with x. Ding! We got it both ways. Those are indeed inverses of each other. Okay. That's how we found it algebraically. Let's do real quickly and see how they do it and see if there's any difference. Okay? First they did a graph. Okay? We didn't do the graph. Okay? Wait a minute. The problem is that's not the same function, is it? Okay. This is the one we did because they told us. This is the one that's in the book, which is different from that one. So next time we'll come back and do the one that's in the book. You did the one that they had on the slide, which was not the one in the book. I wasn't paying attention. So we'll come back and do the actual example 6 next time. Okay? Not the one that's in the book. I mean, not the one that's on the slide set, but the one that's in the book. So, sorry about that. Oh, man, so sorry. That means we won't have the test on Thursday. It'll be next Tuesday. Because what we have to do yet is example 6 and 7, and that's going to be it. Homework exercises include any of the odds 7 through 13. They're all at Calc Chat. 9's at Calc View. 15 or 17, they're both at Calc Chat. 15's at Calc View. 19's at Calc Chat. Okay. Any of the odds 21 to 31, they're all at Calc Chat. 23's at Calc View. 33's at Calc Chat. 35's at Calc Chat. 37 and 39 are at Calc Chat. 41 and 43 are at Calc Chat. 41's at Calc View. Any of the odds 45 to 53, they're all at Calc Chat. 45's at Calc View. And then 55 through 69, we will, and those are all at Calc Chat. 61's at Calc View. Yes?
For the notes for the test, can we do the front and back of a piece of paper?
Absolutely.
Or just the front?
Yeah. Whatever you want to do. Yeah, on a piece of paper.
What do you have, like, James said, can you think of any videos you can watch that can help?
Okay, I can't hear you.
Oh, James said, do you have, like, any videos, like, you can look back on?
Yeah, I've been recording every video. Yeah, it's all on YouTube videos on Blackboard. Okay, and then there's some other sources I put on Blackboard too. You can look at those too. All right, by the way, I should have said this while everybody's in here. I think I said it before. You cannot take the test next Tuesday until you turn in the quiz, and most of you are turning that in right now, so that's great.
Can I ask questions?
Sure.
About the quiz? I'm having trouble with these last ones. And for this one, I'm able to plug in that first part of the quotient thing.
Okay.
But for this, it's f of -1 and this is f of y.
Okay.
Would those still be the same?
Yeah, you just put in, that's not a -1, it's minus f of 1.
Yeah.
You just put in a 1 here, 1 there, and 1 there, and see what you get.
Oh, so do I plug in the one here first, then I put it in?
Yeah.
Okay. Sorry, I'm trying to find where I was at.
I've had this for like a whole month, so I just kept forgetting to
Oh, good. Thank you so much.
And for this one, I'm just confused about like this math right here. How do I get rid of like an x squared and an x?
Okay. Let me see which one this is. 8.
Oh yeah, that's 8.
Right. Okay. Find the zeros, the function algebraically. Okay. Now, that's a ratio of two numbers, right?
Mm-hmm.
How can that ratio equal 0? If you have a fractional form, something over something, how can that be 0?
X can't equal 0.
Only if the numerator. Okay, x can't be equal 0, that's for sure,
Yeah.
because that's in the denominator. Okay, that's out.
Mm-hmm.
But the only way for this expression to be 0 is if that numerator is 0.
Okay.
Because it doesn't matter what the denominator is, as long as it's not 0, that's not going to matter. 0 over 7,485,316 and a third is going to be 0. Okay, so if that numerator is 0, your whole function is 0.
Okay. Am I able to turn this in Tuesday before the test?
What's that?
Am I able to turn this in Tuesday before the test?
You can. It'd be better to get it in Thursday so I can get it graded and maybe
yeah.
back to
I'm
you.
sorry, I thought today
Yeah.
was Thursday. I
Yeah.
can turn it in then.
Wishful thinking. Okay, right.
Can there be more than one page of notes I can bring in?
No, just a single page. Yeah, so condense it to one. Yeah.
So, for the test, the quiz,
Thank you. Say again.
for the test,
Yeah.
you say it will be equations, or can it be like, when the
No,
division
anything
is-
you want to write on a piece
anything,
of paper.
just one
You
sheet,
can write a
right?
sonnet. Yeah, yeah,
Just one
right.
sheet.
Yeah, one
Front
9.5 by 11. Yeah, front and back. Yeah, not one of those sheets. Okay. Okay. All righty.